Okay, everyone join. Welcome, everyone. This is Benito Marcote from JIVE, and I'm happy to welcome you on behalf of the organizing committee to these online seminars sponsored by the European VLBI network that we focused on high-resolution radio astronomy. So today we will have the pleasure to listen to Sandor Frey, or Santa Claus, as you may see, that will tell us all the secrets to achieve very high precision astrometry, thanks to both Gaia and VLBI. But before that, I would like to start mentioning a few logistic points. So first, you will be muted throughout the presentation, but then you are invited to type at any time any questions that you may have to the speaker, preferably through the Q&A section that you may see here in Zoom. Or if you are watching it through YouTube, feel free to post your questions in the chat. We will also take a look there. There will be a discussion section right after the seminar, the talk. So there is where we will address your questions there. And Sandor will be happy to answer them. And we will have enough time to ask most of the questions that you have there, but of course, we will try to end up at the hour. Try to please write your questions clearly and keep them short, because we only have a limited time, and everyone will be happy to participate. And you can also raise your hand if you want to make the question yourself. We will aim to get as many as your questions as we can. And we apologize in advance if the questions are not among those that we have time to answer. And now Javier Moldón will introduce our today's speaker, Sandor Frey. Javier.
Okay, thank you, Benito. So welcome, Sandor. Sandor Frey is a senior research fellow at the Konkoly Observatory, sorry for my pronunciation of the Hungary names, of the HUN-REN Research Centre for Astronomy and Earth Sciences in Budapest, Hungary, where he leads a small but active radio astronomy group. He obtained his PhD degree at the Eötvös University in Budapest in 2001, and the thesis topic was VLBI studies of extremely distant radio quasars, one of his main scientific activities until now. Among other things, he was involved in VLBI studies of various types of radio-emitting active galactic nuclei. He has been a user of the EVN for 3 decades and served as a member of the EVN program committee between 2014 and 2017. So he's a really active user of VLBI and in particular of the EVN. Today, Sandor will share some key insights about the state-of-the-art optical and radio astrometry with sub-milliarsecond resolution, and how this enables new AGN science once you are able to align the optical and the radio celestial reference frame. So, Sandor, when you're ready, you can start. Thank you.
Thank you very much. I'll start sharing my screen and we will see if it is working. Is it okay?
Yes, we can see it.
Yeah.
Perfect. So thank you very much for the invitation. And it's a bit scary because I see many people in the audience who are probably better experts on the topic than I am. But I'll try to do my best. The topic I choose is quite popular nowadays, in the last decade, I would say, because today we reach the point when optical and radio astrometry can provide comparable accuracy. But before starting with my topic, I couldn't resist putting this historical image there, because it was almost exactly 30 years ago when I spent some time at JIVE. And this was the JIVE Season's Greetings card, a photograph, which was taken maybe in November. And in the background, what you see is the JIVE correlator. That time, the new building was under construction. So this signifies my at least 30 years of working with VLBI and with EVN in particular. And of course, you can try to recognize familiar faces in this group photo in an earlier edition. Okay, so I was told that the good presentation starts with explaining the title. So there is a word in the title, which is astrometry, which is simply speaking is positional astronomy. But I asked ChatGPT what astrometry is, and I got this answer here, which is quite reasonable. So astrometry is working with the positions and motions and the distances of celestial bodies. This includes measuring parallax for distance, tracking proper motions of stars, and as we will see, even extragalactic objects, supporting spacecraft navigation, contributing to the celestial reference frame, and that's what astrometry is. And in fact, astronomy was equivalent to astrometry for many centuries in the past, before spectroscopy came into play and astrophysics started. This is a picture, a history of astrometry in a nutshell. This is taken from an ESA website about Gaia, the latest and so far the best ESA astrometry mission. But as you can see, this deals with optical astrometry. Going back to Hipparchus, second century before Christ. So astrometry is really a very old branch of science. This plot shows how the accuracy of position and parallax and proper motion measurements developed over like 22 centuries from Hipparchus. The vertical axis is scaled in arcseconds up to today in the Gaia era. But of course, this is also made for optical astrometry, so it doesn't include radio. And the nice thing is that I will speak about things connected to astrometry which are not even mentioned by ChatGPT. So we can actually teach artificial intelligence in a way. So starting with introducing very briefly in a nutshell the modern astrometry, I of course start with VLBI. Most of us know VLBI very well. So this cartoon on the right shows the basic principle of astrometric VLBI measurements. So we have the baseline between two distant radio telescopes, and we have a quasar on the sky, for example, in the direction marked by this unit vector k. The baseline vector is b, and the basic measurable of astrometric and geodetic VLBI is the time delay between the arrival of the wavefront between antenna 1 and antenna 2, and also the time derivative of this delay, the delay rate, and that forms the basis of all astrometric and geodetic VLBI measurements. Of course, the life is not as simple as indicated by this formula, because we have atmosphere, we have uncertainties in Earth's rotation, and have delays in the electronics of the antennas, but the principle is this. VLBI started in the 1960s, and nowadays these kind of measurements are taken, are organized by an international service. It's called IVS, International VLBI Service for Geodesy and Astrometry, and this world map indicates the locations of different VLBI stations participating in IVS programs. It was almost 30 years ago when the International Astronomical Union decided to switch the fundamental reference frame into something which is realized by VLBI measurements. This is the International Celestial Reference Frame, or ICRF. And the first edition of ICRF was based on a bit more than 200 radio sources, extragalactic radio sources, quasars, basically distributed all over the sky. And in subsequent years, there were improvements of ICRF, which involved a massive observational work and also theoretical work. The second edition of ICRF came out in roughly a decade ago. And nowadays we live in the era of ICRF3 with roughly 2.5 thousand extragalactic objects, and the color scale here indicates the positional error of these sources. But in the course of these ICRF works, it turned out that some of these quasars or active galactic nuclei, which emit radio, they are not exactly stationary on the sky. At the first approximation, we would think that if we have an object very distant, billions of light years far away, they should not show any measurable proper motion in the sky. But it turns out not to be exactly true. There are some sources which show quite significant changes in their position. This is one of our favorite calibrator sources, bright source 4339.25. And as we can see on the left, especially its right ascension changed a lot during the decades, and it's significant. This plot also shows how the accuracy of the measurements improved over the decades. One would naively think that this excursion of right ascension, which is well within a milliarc-second, is connected to the structure of the radio source, which is elongated in the east-west direction. And indeed, the changes are larger in right ascension. There are a few of these sources which were actually taken out of the defining sources of ICRF at later editions. Back in 2011, we performed the first study which tried to find connection between the radio structure, the milliarc-second scale radio structure, and the apparent proper motion direction of certain sources in the sky. That time we had a reliable data, significant proper motions for around 60 objects. And we found that actually most of those proper motion directions align quite well with the jet direction of the source. But there were a few outliers, exceptions, including this nicest example, another favorite source, OJ287, which is probably the best binary AGN candidate, with closely separated two supermassive black holes orbiting around each other. And for OJ287, it turned out that the proper motion direction, which was derived from decades of VLBI positioning observations, is actually almost perpendicular to the jet direction, which we see here on the left in this 80 Hz VLBI image. So how is it possible? We proposed a solution that the jet direction might be actually turning sharply within this resolution beam. And indeed, not much later, 83 GHz VLBI images of this source were published, and it turned out that the innermost jet structure is actually very well aligned with the proper motion direction. And you remember these proper motions are at the order of roughly 10 microarcseconds per year. So it's really tiny number. So this way, the general picture was saved, because even for OJ, we could prove that the proper motion direction is aligned with the jet direction. Nowadays we have more data, and there are some very interesting sources popping up. This is one recent example. We published it not long ago in a paper led by Oleg Kitov. Actually, the papers I was involved in, they are marked with a green background, so you can follow my work. So what happens with this source, which was thought to be a high redshift quasar, now it turned out that its redshift determination was not reliable enough, so it's rather a lower redshift quasar, but doesn't matter. It apparently follows a spiral-like pattern in the sky. Again, watch the scale. This is well within a milliarcsecond. It's some tenths of milliarcseconds, the amplitude of this kind of motion. Of course, we don't have enough data, just maybe one period or a little bit more. So don't take it for granted that it is a spiral moving thing, but it is possible. Even more recently, there was another source, JO2404, which provided even a better evidence for such kind of periodic motion, both in right ascension and declination, and with the same period, basically. So it was significant, and we could even speculate whether these motions are caused by a subparsec separation binary supermassive black hole. But of course, the jury is still out, but it just indicates that the precision which we reach in radio astrometry is now allowing us to make this kind of studies, which would have been unimaginable even 10 or 20 years ago. Switching to optical astrometry, we had Gaia, which worked for more than a decade, and this year it stopped operating. Of course, the data are still being analyzed, and new data releases will come. So in a way, we are still living in the Gaia era. Gaia was an optical astrometry mission of the European Space Agency, orbiting around the L2 Lagrange point of the Sun Earth system. The big thing in Gaia, well, one of the big things, I mean, there were many big things in Gaia, which I'm not prepared to show you. But from our point of view, the best thing in Gaia was that for the first time in the history of high precision optical astrometry missions, it was able to directly observe extragalactic sources, quasars, and this built up a large sample of cross-matched objects, which we can use to directly link the optical and the radio reference frames in the sky. This was not the case for Hipparcos, for example, the predecessor of Gaia. But now we have more than 1 million quasars, which are competently identified in the Gaia data. And recently there was a catalog called Gaia constructed, which cross-checked the Gaia detections with other surveys and found 1.3 million quasars. Actually, this cartoon of a quasar on the left is only valid for a small fraction of these objects, because it has jets which produce the radio emission, synchrotron radio emission, which we can detect with radio telescopes and probably with VLBI. A recent study led by Nestor Arzanov, a PhD student, found that by cross-matching this Gaia catalog with the radio catalog, the VLA Sky Survey catalog, the radio loud fraction of quasars is about 8 degrees. Nothing surprising. This is what we already knew from earlier studies, but this is the largest sample we could study in this way. So let's go to the history. Just before Gaia, with my former student Gabor Orosz, who recently finished his term as a JIVE support scientist. It was his master's thesis study. We took ICRF2 positions, the best VLBI positions that time available, and Sloan Digital Sky Survey. That was a large catalog before Gaia. And these dots actually represent the positional accuracy of these. So this is ICRF accuracy, this purple dot, and this yellow one, which didn't fit in the screen, was representing the Sloan position. In other words, positional accuracy. In other words, ICRF positions were just very much better than the optical ones. And what we did, we compared the positional differences between ICRF2 sources, which had optical counterparts in Sloan, and found that, of course, there is roughly a 50 or 60 milliarcsecond positional accuracy of Sloan. But more interestingly, we found a big, relatively large number of sources with outliers in terms of optical and radio distance. That was about 4% of 50 sources in the sample. And these are all peculiar cases, and all are interesting from some astrophysical point of view. For example, they can be gravitational lenses. We actually identified gravitational lensing systems that were already known. They can be very peculiar complex jet structures, or even dual or recoiling active galactic nuclei. So that was a kind of teaser what we could expect when Gaia comes, and when then Gaia positional accuracy is actually comparable to the VLBI positional accuracy. And indeed, after the first Gaia data release, people started to compare optical and radio positions. And interestingly, they arrived at very similar plots. Of course, the peak of the distribution, the positional differences was much smaller, reflecting the better accuracy of Gaia compared to the Sloan survey. But more interestingly, we still have these outliers, which are statistically significantly above the thing which one would expect purely from statistical differences between the two catalogs. This can be up to 10%. And since then, there are very nice studies. Some of them are listed here, which investigate how the optical and radio positions of the same sources differ. On the left, there are just two examples. And it turns out that these differences are not random. But first of all, we should clarify what we see in optical and what we see in radio. Are they the same things physically or not? Certainly not, because in the optical, of course, we see optical emission, which in the case of an AGN comes from the accretion disk and maybe from the jet in the form of synchrotron emission, which falls in the optical waveband. On the other hand, in the radio, we see basically the jet and the jet features, and in particular, the most compact feature of the jet, the optically thick emission at a given frequency, the base of the jet, which does not necessarily coincide with the centroid of the optical emission. And indeed, studies show that if we take a look at the direction of the vector between the optical and the radio positions, then we can see basically two peaks. These plots from the left to the right is the increased reliability of the positional differences. So for the most reliable measurements, we can see these very distinct two peaks at 0 degrees and the opposite 180 degrees. So it means that the quasars, radioactive galactic nuclei, tend to have their radio and optical position offsets either downstream of the jet or upstream of the jet, but in terms of direction along the jet. Where we have the downstream differences, we can infer strong optical synchrotron emission in the jet. Once again, I have to emphasize that we don't have the resolution, especially in the optical, to actually resolve the optical synchrotron emission of the jet. We do know some very nearby AGN with optical jets, but in general, at cosmological distances, we are just unable to resolve these jets. Still, thanks to the astrometry, the optical and radio astrometry at this level of precision, we can study the physics of the optical jet synchrotron emission. The upstream difference can be caused by a dominant accretion disk. And if you take a look at this nice paper by Clubin et al., you can even find that different categories of different types of AGN behave in different ways in this respect. So the bottom line is that we can use astrometry, optical and VLBI astrometry to study AGN physics at the tiniest linear scales. What else? These offsets are useful for identifying special types of active galactic nuclei. I just show you some examples. One is the so-called compact symmetric objects. These are young AGN with expanding radio jets and lobes. The age of CSOs is some hundreds of years or thousands of years. So they are really young. So they are recently turned up active galactic nuclei, new jets, and they are expanding in the environment in the host galaxy. And these are fundamentally different objects from blazars, which we usually observe with VLBI, with a one-sided core jet structure with a bright core and some usually fainter jet components. Just based on VLBI imaging, these are sometimes very difficult to identify. But if we can compare the positions, the structure with the positions measured by Gaia, like on the left side of the image, this is a given single source at different radio frequencies, VLBI images, and the cross marks the Gaia position. So if we can compare them, we can pinpoint the location of the AGN, basically the accretion disk, so around the black hole. And if it doesn't coincide with any of these symmetric features in the radio images, then we can be sure that these are not core jet sources, but rather compact symmetric objects. A recent study led by Tao from Shanghai, and it's about to be published in ANA maybe this week or next week. We did a large, we investigated a large sample of 40 CSO candidates and could confirm that 20 of them are real CSOs, just based on comparing the VLBI structure images with accurate Gaia positions. And of course, then we can also make spectral index images as seen on the right to have this kind of classification. But there's a huge potential in Gaia VLBI astrometry in identifying these CSOs, these young peculiar active galactic. Another case is another recent paper by Popkov and al. And others. They compared the Gaia positions with the VLBI positions and tried to select sources where the Gaia coordinates do not coincide with the brightest component, which we usually believe is the core, but another feature in the VLBI structure. And they found 35 sources, and they turned out to be very interesting objects individually because they contain a low brightness temperature core, which is not the brightest feature necessarily in the VLBI image. So it's again a nice tool to find peculiar types of sources. In principle, it would allow us to find dual active galactic nuclei as well, but none of them turned out to be a dual AGN so far. Another interesting line of research is that because we have increasingly long database for VLBI astrometric measurements. There are a couple of sources which show huge and relatively quick change in their astrometric position. Like, for example, this source which I show here is CTA21, and within 2 decades or so, it changed its position by several tenths of milliarcseconds, which is huge compared to the sub-milliarsecond accuracy of the position measurements. And if we compare 2 images of the same source taken at this time in the 1990s and more recently, we can actually figure out what happened. There was a new compact and bright component appearing sometime somewhere in between these dates where we unfortunately don't have data, and then it caused the shift of the radio peak to a position which is about 30 milliarcseconds far away from the previous one. Another nice example, one of my favorites, because at the time when I started my career in VLBI, with Zsolt Paragi, we imaged this very famous, very bright source, 3287, which was one of the most popular VLBI targets in the early days of the technique. And I remember the literature, there were debates on whether where the core in this very complex radio structure is located in the source. 3C287 again produced some apparent jump in the radio position, astrometric position, and very recently with the EVN we made a phase reference observation of this source, and it is seen on the right. And it turned out that the new so-called new VLBI position is actually located quite far away, like about 150 milliarcseconds far away from the well-known radio structure of this source. And it also turned out that this new component, which is probably fading away, is actually coincident with the Gaia position very well. The Gaia position is marked with this big green cross. So, in other words, we don't have to look for the core of this AGN in this extended structure. Most likely, the core is actually here, which we have never seen before, and that is also coming from astrometry. And there are lots of other possibilities to look for peculiar objects with astrometry. I just list here a few. If you can take a look at how the Gaia astrometric positions are varying in time. This technique is called barstrometry, so variability in astrometry. Then you might find interesting sources, for example, like dual active galactic nuclei, gravitational lensed sources, gravitationally lensed objects. Again, you can look for multiple peaks in the Gaia light profiles, so within the PSF of the Gaia, that also can provide us with candidates for dual AGN, for example, and that and those sources can actually be followed up by VLBI imaging if they are radio loud, because VLBI is the only technique which we can use for such a high resolution and direct imaging observation. And also, a very recent paper is still in press, but can be found on archive, one can look for those sources which are small separation, Gaia detections, and radio loud, and can try to find dual radio emitting active galactic nuclei. So VLBI imaging is a tool which can be used for following up these peculiar candidates with high resolution. And in the last 1 minute or two, just a look into a very short look into the future. Gaia has its fourth data release scheduled for next year, and for the first time it will include time series data, so we can follow how the coordinates of certain objects were changed over time, and that could open up new possibilities for identifying astrophysically interesting objects. That is the near future. So to finish up, I collected some take-home messages. The important thing is that we live in the era of precision astrometry, both in the radio and optical, and they reach the same sub-milliarcsecond accuracy for the first time in the history of astronomy, and that opens up lots of interesting possibilities for AGN astrophysical studies as well. Another interesting thing is that AGN positions, which are different in radio and optical, are quite widespread at basically any given level of accuracy. So these are again very nice sources by themselves, and also statistically this can be used for jet studies in optical, which would not be possible at all using the limited imaging resolution which we can use in optical. Again, and if you are interested in this field, it's probably, or for students, I think it's the right time to start research work in this field, because that has still a good perspective. So stay tuned for more discoveries and actually make your own discoveries yourself. And to finish up, I would like to thank my collaborators. Very few are listed here, and I thank you for your attention, and I'm happy to answer any questions if I can.
Okay, thank you very much, Sandor, for your talk. It's impressive to see how aligning these two very different wavelength data can provide much more information when you combine them. Okay, so anyone that has questions, you can write them in the Q&A section, or the chat. If one is better in the Q&A, or in YouTube, you can write it in the message box, or you can raise your hand if you want to speak the question directly. Okay. Okay, for the moment, I don't see any questions, so I will start myself with a question. So, Sandor, do you have any practical recommendation for cases like maybe we have observations from a decade ago, from years ago, phase reference observations, so we have the correlation position of the phase calibrator, and we want to see how it matches with current Gaia, for example, DR3, or in the future DR4 measurements. So what would be the practical way to try to align older observations with newer one? It's just a shift with a more up-to-date position of the phase calibrator. Is anything else that we should do to try to align this already observed data?
That's a very interesting question. So if your phase calibrators, so if I understand correctly, you are speaking about a phase calibrator, which might change its position
Yes,
over time, and that would affect the position derived for the target source. Or I didn't understand correctly.
Yeah. That's is just to try to align the astrometry that you have from previous, for example, ICRF references.
Yeah, still the best thing is to look into ICRF, but some of these jumping sources I showed you, there are not too many of them. So I don't want to make you worried that your phase reference observations are crap, because this is a small minority of sources. But some of them might have entered an earlier edition of ICRF because there were very few observations, and maybe just one epoch or two epochs. And that time, one of the components was brighter than the actual core. And that was the reason why this source entered with the wrong coordinates, not current coordinates into the database, even though that was the other radio position, the core position. That was also another radio component. So the practical advice is that look into ICRF editions and look back to the earlier editions to see if the positions have changed for a given source or not. But in most cases, this is not a problem. So they are not jumping.
Okay.
Too much.
Great, thank you. I think Benito has a question from YouTube.
Yes, Prashant was, first congratulating you for the nice talk. And then he was asking if there are examples where radio and optical peak positions are actually at similar locations, like, for example, in nearby radio quiet quasars.
That's the usual case. I mean, they are usually within the uncertainties. They are similar. If I go back to this distribution plot, most of the sources are behaving like what you expect from some random differences between optical and radio. But for us, the interesting objects are these, which have significantly larger offsets. Of course, if I would like to construct a good reference frame and a good reference frame tie between optical and radio, I would definitely pick these ones because they are statistically the same. But if I'm the one who is trying to find interesting sources in astrophysical point of view, I would like to pick these ones in this tail of the distribution.
Do you have
I'm not sure I answered it.
Yeah, I think that was the answer. Do you have some rough estimation of which percentage of sources so in course for which ones don't?
It's a few percent, like up to 10% of the sources are off. But the interesting thing is that when we did it with Sloan, which is obviously not the right thing because Sloan has much worse accuracy, but still on this level, like several hundreds of milliarcseconds, we still had 4%. So that's like 5-10%. You can always find these objects, and these are most likely not chance coincidences because these quasars are not populating the sky so densely that you have an unrelated background foreground quasar within a few hundreds of milliarcseconds. That's almost impossible statistically.
Thank you.
Okay, so we have a question from Ronald Dreamer. He says, very nice talk. Perhaps I missed it, but do sources with proper motion seen in VLBI also show proper motion in Gaia?
That's a good question, and that's what I would expect from the data release 4, because so far Gaia positions are not they are not time dependent. So we don't have time dependent data set. So we don't have a time series of positions. Yeah, that will be one interesting question to look for. But you know, Gaia is like it observed for a little bit more than 10 years, so it must have been a very large proper motion to detect from Gaia data. By VLBI measurements for very prominent bright sources, they are available for many decades now. So it's easier to find a trend, a small trend, a few tens of microarcseconds per year in VLBI data still. But yeah, that would be interesting to see if there are quasars with detectable proper motion in Gaia data.
Okay. Thank you. The next question is by Wara Chamani. Nice talk. Are the core shifts of the phase calibrators considered for absolute astrometry?
That's a good question. I didn't speak about core shifts. Yes, this should be taken into account, but these effects, what I showed you is actually these are larger than the opacity driven core shifts in AGN cores, which is in the order of tens of milliarcseconds, if I'm correct. Somebody can correct me if I'm wrong. So these are much larger offsets than the core shift. But of course, core shift between optical and radio, if we are speaking about jet synchrotron emission, that is also involved in this kind of differences which I showed you. But these are larger, so these are on milliarcsecond scales. But indeed, if you have studies of a given object, if a given object, you have to try to take into account the core shift always.
Thank you for the answer. I don't see more questions in the chats on YouTube. I have one additional question. So, can you comment a bit on the uncertainties or the accuracy or the differences between the two reference frames as a function of different positions of the sky? So, it's, for example, in the northern sky, in the southern sky, or there are regions of the sky that has peculiarly high or low uncertainties when matching. I mean, matching the reference frames.
Yeah, of course, Gaia itself is a spacecraft, so it doesn't care about hemispheres. So it's the coverage of Gaia is the same at both hemispheres, but it does care about the galactic plane because it doesn't look through the galactic plane. So to see the extragalactic sky behind the galactic plane is much more difficult. But if you take a look at an ICRF plot like this, you can see that the southern hemisphere is still less densely populated with reference or actually VLBI studied sources. This is not because there are no quasars in the southern sky. That would be a very high conspiracy from the universe. But it's not true. But the reason is that in the southern hemisphere we do not yet have so many observing facilities. So the number of observations is obviously much smaller in the southern hemisphere, and that causes these errors larger than in the well studied northern hemisphere. So the northern hemisphere, we have a networks have a reach down to roughly -40 degrees declination, and what is below that, it is still to be studied. And I know that there are serious efforts to densify the reference frame, the radio reference frame in the southern hemisphere, deep in the south. So that's the technical reason for having less accurate positions and less sources actually observed in the southern sky.
Okay, thank you very much. I think we don't have any other question. Benito, do you have any announcement to make to close the session?
Yeah.
Otherwise, well, before finishing, just thank you, Sandor, and thank you for
the invitation, and have a nice Santa Claus and the rest.
That's good. Thank you. Okay, Benito.
Yeah. Thank you for the nice seminar, Sandor. I only have a quick announcement. So we will continue with the seminars next year, but we still don't have fixed dates. So keep tuned, and then you will see the announcements early next year. But then meanwhile, you may have received already the first announcement of the EVN Symposium and users meeting that will happen in 2026 next year in September. This time we will be happy to meet in Manchester. They already have the website and all the information. So please keep on and then save the dates if you want to join the EVN Symposium there. It will be a really nice place to see all the science that can be done on VLBI. So it's a natural in-person continuation of these seminars. And so far, this is all from our side. So thank you very much for joining. Thank you, Sandor, for the nice talk. And then see you in the next seminar.
Thank you. Bye.